At the bottom of the Mariana Trench, 11,000 meters below the surface, the water column exerts 15,750 pounds of pressure per square inch. That is the structural equivalent of trying to hold up a modern steel skyscraper on your own shoulders. Yet life thrives in that crushing abyss. We reside on a planet covered 70% by water, and we spend billions staring up at the stars looking for alien life. But the ocean remains our own immediate, terrifying unknown.
The contradiction there is profound. The National Oceanic and Atmospheric Administration points out that while global initiatives have mapped about 26% of the seafloor using sonar, mapping is a far cry from exploring. When we talk about physical exploration, sending cameras or human beings down to document the environment, we have covered less than 10%. Many marine biologists estimate the number of human-explored areas sits closer to 5%. We possess comprehensive topographic maps of Mars, but our own ocean floor remains a mystery.
I want to push back on the Mars comparison, even though it appears in almost every discussion about ocean exploration. Mars is a dry, static rock with a thin atmosphere. We can point satellites at it and bounce radar off the surface without interference. The ocean, by contrast, is a dense, dynamic medium that absorbs light and radio waves. It makes logical sense that we have not explored it. The barrier is physics. But I suspect there is also a psychological barrier. Space represents a clean, upward trajectory for human ambition. It evokes a sense of manifest destiny. The ocean represents a descent into darkness, claustrophobia, and immense crushing weight. It does not offer the same heroic narrative.
That touches on the core reason why the engineering challenges of the ocean are so unforgiving, and why funding lags behind space exploration. In space, an astronaut or a probe deals with one atmosphere of pressure difference, the difference between the inside of the suit and the vacuum of space. At the bottom of the ocean, a submersible deals with over 1,000 atmospheres of pressure, pressing inward. Water finds every weakness. It corrodes metal, shorts out electronics, and exploits microscopic flaws in structural holes. You mentioned the weight of a skyscraper earlier. That is a factual comparison. The pressure at the bottom is about 1,086 bar. If you placed a standard foam cup outside a submarine at that depth, the ambient pressure compresses it down to the size of a thimble in a fraction of a second.
And yet, biological organisms survive there. That is the part that defies human intuition. If a steel submarine struggles to withstand the environment, how does a living creature exist? We assume biology requires delicate conditions.
Nature engineered workarounds for the pressure. Take the Mariana snailfish, which lives at depths over 8,000 meters. It is a vertebrate, but it does not have a hard skeleton or air-filled swim bladders that would collapse under pressure. Its bones are flexible cartilage. What matters most is that its cells contain high concentrations of a molecule called TMAO. This molecule stabilizes proteins, preventing the immense pressure from crushing the cellular structures and stopping chemical reactions. The fish operates on a different biochemical level to survive the weight of the water above it.
That brings up the sheer hostility of the environment. Beyond just the physical weight, there is the absence of light. We think of space as dark, but space is filled with starlight, galaxies and photons traveling without hindrance for billions of years. The deep ocean is a different kind of dark. It is a suffocating void.
Sunlight penetrates the ocean in strict layers. The top layer, the epipelagic zone, gets enough sunlight for photosynthesis. But once you descend past 1,000 meters, you enter the aphotic zone. No sunlight reaches there at all. It is darker than the darkest cave on land. For the creatures living down there, eyes are often useless. They navigate and hunt using bioluminescence, creating their own chemical light, or they rely on extreme pressure sensitivity and smell.
Which turns the deep ocean into an
alien universe. For a long time, biological consensus held that all life on Earth relied on the sun. Plants perform photosynthesis, herbivores eat the plants, and carnivores eat the herbivores. The sun was the engine. Then, the discovery of hydrothermal vents in the late 1970s shattered that paradigm.
This discovery altered biology at a fundamental level. Researchers found these towering chimneys on the seafloor, spewing superheated, toxic black smoke into freezing water. By all known logic, it should have been a dead zone. Instead, they found complex ecosystems, giant tube worms, blind crabs, and unique bacteria thriving in the extreme heat and toxicity. These organisms do not use photosynthesis. They use chemosynthesis. The bacteria convert the toxic hydrogen sulfide from the vents into organic matter. They survive independent of the sun, drawing their energy from the internal heat of the Earth itself.
That proves life does not need a warm, sunlit rock to exist. It suggests that if we find life on other planets, like Jupiter's moon Europa, which has a subsurface ocean, it will probably resemble these deep-sea extremophiles. The ocean is not just a part of Earth. It is a testing ground for astrobiology. We are looking at a preview of what extraterrestrial life might look like.
The National Oceanic and Atmospheric Administration estimates that 91% of ocean species remain undiscovered. We are talking about millions of unidentified organisms. We discover new species of deep-sea corals, bizarre jellies, and ancient sharks on almost every deep-water expedition. The deep ocean is a separate universe, operating by rules we are only beginning to grasp.
Let us pivot from the physical hostility of the ocean to the human psychological experience of it, because there is a massive contradiction here. We just established that the ocean is a pitch-black, crushing void filled with alien creatures and toxic vents. It is a place that kills humans in seconds. Yet if you ask someone where they go to find peace, they will say the beach. People buy white noise machines that play the sound of crashing waves. We associate the ocean with profound tranquility. How do we reconcile the terror of the deep with the therapeutic effect of the shore?
That contradiction sits at the center of a concept called blue mind theory. The late marine biologist Wallace J. Nichols spent his career studying the neurological and psychological impacts of water on the human brain. According to his research, being near, in, on, or underwater induces a distinct state in our brains. It lowers cortisol levels, reduces our heart rate, and shifts our brainwaves from a state of high alert to a state of relaxed focus.
I question whether the water itself is causing the chemical shift, or if it is just the absence of urban stress. People go to the beach on vacation. They are not at work, they do not have their phones. It seems logical they feel relaxed. Is it the water, or is it just the escape from the modern environment?
Nichols and other neuroscientists used fMRI scans and EEG machines to monitor brain activity in the presence of water, to isolate that specific variable. The sound of water alone is processed in the brain in a way that provides a non-threatening sensory environment. In our day-to-day lives, we exist in what Nichols called a red mind state. This is an anxious, overstimulated condition driven by screens, traffic, and constant demands. The ocean acts as a sensory reset. The visual pattern of the waves rolling in provides a gentle fascination. It occupies the brain just enough to prevent rumination, but not enough to cause mental fatigue.
What about thalassophobia? The fear of the deep ocean is a documented and common condition. If human brains are hardwired to relax near water, how do we explain the visceral panic many people feel when they look at open water or imagine the abyss?
Thalassophobia represents the ultimate evolutionary respect for the power of the ocean. The blue mind effect occurs at the shore, in shallow water, or when observing the water from a safe vantage point. When a human confronts the open ocean, the brain recognizes a lethal environment. We are terrible swimmers compared to marine life. We cannot breathe underwater. The fear of the deep is a survival mechanism. It is the red mind firing off alarm bells because the deep ocean is a realm where we have no control. It highlights the dual nature of water as both a life-giving force and a destructive power.
It is an evolutionary anchor, either way. Human beings evolved near water out of necessity. We need fresh water to drink, and coastal areas provided abundant food sources and temperate climates. It makes evolutionary sense that our nervous system rewards us with a dopamine release when we find a safe body of water. It signals survival.
The sound of rhythmic water is, in a literal sense, the soundtrack of human survival. Nichols also argued there is a connection that goes beyond basic survival mechanics. Our bodies consist of about 60% water. Our brains sit in a bath of cerebrospinal fluid. We begin our lives suspended in amniotic fluid. Water is the fundamental medium of our existence. When we look out at the ocean, there is a profound, unconscious recognition of our origins.
The data seems to back up the health outcomes. The Ocean Conservation Trust in the United Kingdom uses the Blue Mind ethos for community well-being projects. They take people experiencing poor mental health into ocean spaces, doing activities like rock pooling or visiting aquariums. Their data shows substantial improvements in well-being and a decrease in anxiety. This therapeutic value contrasts with the enduring mystery of the depths. I look at the historical timeline of ocean exploration. We sounded the Mariana Trench during the Challenger expedition in 1875 using a weighted rope. It took them hours just to let the rope hit the bottom. In 1960, Don Walsh and Jacques Picard descended in the bathyscaphe Trieste. They spent a matter of minutes at the bottom, surrounded by tons of pressure, before coming back up. Since then, almost no one goes down there. We visit the abyss just to prove we can, rather than to stay and understand it.
The economics of deep-sea exploration are tough to justify for governments. Space exploration yields tangible communication and surveillance technologies. Deep-sea exploration is harder to monetize, though that is changing with the controversial push for deep-sea mining. Companies want to harvest polymetallic nodules from the seafloor, which contain cobalt and nickel needed for electric car batteries. We are preparing to mine and industrialize the deep ocean before we have even classified the species that live there.
We risk destroying an ecosystem before we even map its basic functions. The ocean functions as the primary carbon sink for the planet. It absorbs excess heat and carbon dioxide from the atmosphere. We treat it as an endless void, a place to dump our waste or extract resources, forgetting that it is a fragile, interconnected biological machine. The extremophiles at the hydrothermal vents might hold the keys to new antibiotics or revolutionary industrial enzymes. A mining dredge could wipe them out in an afternoon.
Which circles back to why the ocean remains so mysterious. It operates on a scale that defies human comprehension. The Pacific Ocean alone is larger than all of Earth's land masses combined. You could fit all the continents into the Pacific Basin and still have room left over. The sheer scale breeds a false sense of invulnerability. We assume something that massive cannot be broken by our actions.
It is a crisis of perception. We view the ocean as a surface, a flat blue expanse we fly over in airplanes or cross in cargo ships. We rarely conceive of it as a three-dimensional volume. When we say we have mapped 26% of the seafloor, we are ignoring the billions of cubic miles of water suspended above that floor. The pelagic zone, the open water column, is the largest habitat on Earth. It is filled with creatures migrating up and down every day in the largest mass migration on the planet.
You are referring to the diel vertical migration. Every night, millions of tons of marine life, from microscopic zooplankton to lanternfish, rise from the deep twilight zone to the surface to feed under the cover of darkness. Before sunrise, they sink back down to the safety of the depths to avoid predators. This movement is so massive that sonar operators during World War II mistook the dense layer of animals for the actual ocean floor. They called it the deep scattering layer. It is a biological pump that transfers carbon from the surface down to the deep ocean, keeping the planet stable.
The deep scattering layer is the perfect metaphor for the ocean itself. It is deceptive. What looks like a solid bottom is just a temporary curtain of life. The more we probe the water, the more the floor drops out from under our assumptions. The ocean demands a kind of intellectual humility that human beings struggle to produce. We want to conquer the unknown, but the ocean crushes our machines and consumes our light. It forces us to accept that we are visitors on our own planet.
That humility is essential. The mystery of the ocean is not just a gap in our data. It is a fundamental feature of the planet. Even with autonomous drones and artificial intelligence analyzing sonar data, the ocean will always retain a core of the unknown. It is too dynamic. Currents shift, trenches subduct, and vents collapse and reform. By the time we map one sector, it has already changed.
We began with the crushing weight of the Mariana Trench and the pitch-black void of the abyss, and yet we ended up discussing the neurological peace the ocean provides. It strikes me that the ocean is the ultimate mirror. If you bring a submersible and a spotlight, you find alien horrors and impossible physics. If you bring a tired mind to the shore, you find tranquility and restoration. The ocean reflects our deepest fears and our deepest need for calm, holding both in a delicate, fluid tension.
That tension is the defining characteristic of our relationship with water. It is life-giving and lethal. It is the known surface and the unknown depth.
The ocean will remain the most mysterious place on Earth because it refuses to be just one thing. It is an alien universe right here on our doorstep, vast enough to swallow all our questions. If you found yourself intrigued by the paradox of the ocean today, pass this episode along to a friend who appreciates a good dive into the unknown.
We live on a planet that is 70% water, yet humans have physically laid eyes on less than 5% of the ocean, making it the single most neglected roommate in the history of the solar system.
And that 5% is mostly just tourists dropping sunglasses off the side of cruise ships. The National Oceanic and Atmospheric Administration confirms that more than 80% of our ocean remains entirely unmapped, unobserved, and unexplored by humans. We map the surface of Mars with staggering precision while treating our own seabed like the dark corner of the basement where we shovel gym bags. Mars gets the PR budget, but the ocean holds the actual terror. The depths of the ocean are darker than deep space, and we send billionaires up in rockets instead of down in submarines. Wait, bad example. Very bad example. But the point stands. Space exploration is difficult because of the distance and the vacuum. Ocean exploration is difficult because the ocean actively tries to crush you. The deeper you go, the more the water stacks up on top of you.
Let us break down the Mariana Trench, the deepest known point on Earth. People casually toss around the phrase under pressure when they have a deadline on a Tuesday. The trench redefines the concept. At 36,000 feet down, the pressure is roughly 16,000 pounds per square inch. It is over 1,000 times the atmospheric pressure we feel at sea level. To put a visual on that, it is the equivalent of balancing 70 cars on the palm of your hand, or an entire skyscraper sitting on your chest. And yet, things live down there. We have these delicate, gelatinous blobfish and weird translucent squids just floating around in an environment that would instantly turn a human being into a compressed cube of meat. Those creatures survive because they are not fighting the pressure. Their bodies are filled with water at that exact same pressure. It all cancels out. If you dragged one of those deep-sea creatures up to the surface, the sudden lack of pressure causes them to expand and turn into gooey puddles. They are literally holding themselves together through the power of crushing oceanic weight. We have mapped 26% of the ocean floor in high resolution thanks to the Seabed 2030 initiative, but scientists estimate 91% of marine species are still undiscovered. We're sharing the planet with an entire alien universe. The deep ocean operates on completely different rules. We have hydrothermal vents spewing boiling, toxic soup where giant tube worms thrive without sunlight. They use chemosynthesis to eat chemicals. An entire alien world exists beneath the waves, packed with monsters that generate their own bioluminescent light. And yet, our modern culture treats the ocean as a giant relaxation app.
People download the sound of crashing waves to fall asleep.
The psychological effect of the ocean is a heavily documented phenomenon. Marine biologist Dr. Wallace J. Nichols coined the term blue mind. Blue mind? Sounds like a futuristic energy drink flavor. It is actually the mildly meditative state humans fall into when we are near, in, on, or under water. Nichols theorized that being near water lowers cortisol levels, increases dopamine and serotonin, and activates the parasympathetic nervous system. We stare at a body of water that conceals a dark, freezing abyss of terrifying monsters and crushing pressure, and our brain releases the happy chemicals. The human brain evolved to be in a constant state of high alert, constantly scanning the environment for threats. Nichols calls this the red mind state, which modern society exacerbates with phones, traffic, and noise. The ocean presents a massive, static, unchanged visual field. The rhythmic movement of the waves synchronizes with our brainwaves, giving us a break from the sensory overload of daily life.
Our brains look at millions of gallons of salty death and think, finally, a place where I do not have to check my email. We love the ocean because it is the ultimate mute button on the modern world. Urban planners are now incorporating blue spaces into cities, just to mitigate mental health inequalities. Simply looking at an aquarium drops blood pressure and heart rate. Water provides an immense natural stress relief. We should build a giant aquarium in the middle of every stressful office environment. Just a giant tank of terrifying anglerfish to remind us that things could be worse. We could be surviving at 1,000 atmospheres of pressure in the pitch black.
The irony of the ocean is its duality. The surface provides mental clarity, while the depths remain the most hostile, unexplored frontier on Earth. We are completely mesmerized by the cover of a book we have barely opened. Send this episode to a friend who needs a mental vacation to the deep blue sea.
At the bottom of the Mariana Trench, water pressure equals 50 jumbo jets stacked on a person, dictating the ocean's structure from the surface to the abyss across 5 zones. Those 5 layers define the vertical geography of our planet. When humans look out at the ocean, we see a flat expanse of blue, perhaps broken by waves or currents. We almost never perceive it as a towering, layered column of distinct habitats, each governed by its own unforgiving laws of physics. The transition from the sunlit surface down to the trenches involves drastic shifts in light availability, temperature gradients, and hydrostatic pressure. Eloise, we divide this vast water column into the epipelagic, mesopelagic, bathypelagic, abyssopelagic, and hadopelagic zones. These Greek prefixes map out a descent into absolute darkness. To start, the boundaries separating these layers are not physical walls. They are determined by the behavior of light and water mechanics.
The architecture of the ocean is driven by the limits of solar radiation and the brutal math of water weight. The uppermost layer, the epipelagic or sunlight zone, extends from the surface down to about 200 meters. This is the only slice of the ocean where enough light penetrates to support photosynthesis. Because of that solar energy, the epipelagic zone functions as the engine for the entire marine food web. Phytoplankton thrive here, converting sunlight into energy, which then feeds everything from tiny crustaceans to blue whales. Temperature in this layer fluctuates wildly. According to data from the National Oceanic and Atmospheric Administration, surface waters can reach 36 degrees Celsius in the Persian Gulf or drop below freezing near the poles.
That temperature variation feels unique to the surface. Once you leave the epipelagic zone, the influence of the sun diminishes fast, taking the heat with it. Pressure is another metric that scales in a way most land-dwelling mammals struggle to comprehend. At sea level, we experience 1 atmosphere of pressure. In the ocean, pressure increases by 1 atmosphere for every 10 meters of depth. By the time a diver reaches the bottom of the epipelagic zone at 200 meters, 20 atmospheres of pressure are pushing down on them. 20 atmospheres is enough to crush untreated scuba tanks. Marine organisms in the epipelagic have adapted to this range, but the environmental shift becomes severe just below that 200-meter mark. This brings us into the mesopelagic zone, spanning from 200 to 1,000 meters. Scientists call this the twilight zone. Light still exists here, but it is less than 1% of what hits the surface. It is far too dim to support plant life. This zone is also home to the thermocline, a distinct transition layer where water temperatures plummet rapidly with depth. You leave the sun-warmed surface waters and plunge into a near-freezing environment over a short vertical distance.
The mesopelagic zone seems to function as a biological highway. It hosts the largest daily migration of animals on Earth. Billions of organisms, including lanternfish and various zooplankton, travel up to the epipelagic zone at night to feed under the cover of darkness, then retreat back to the mesopelagic during the day to avoid predators. But recent studies show this zone is no longer just a refuge. A May 2026 study published by the Woods Hole Oceanographic Institution found evidence of heavy, industrial-scale fishing targeting the twilight zone. Commercial fleets have been pulling out significant biomass, including midwater species like pomfrets and snake mackerels, for decades. This undercuts the old assumption that the mesopelagic was an untouched wilderness. The Woods Hole researchers exposed a massive blind spot in global fisheries management. The mesopelagic zone holds more fish biomass than any other marine environment, but for years it was treated as a void on the map. The same institution recently published findings in the Marine Ecology Progress series detailing how apex predators rely on this zone. Using satellite tags, biologists tracked large sharks diving deep into the twilight zone to hunt mid-sized fish like the big-scale pomfret. The twilight zone is the critical puzzle piece connecting the deep ocean ecosystem to the surface food web. Removing massive quantities of pomfrets and lanternfish could destabilize the diet of swordfish, tuna, and sharks that feed near the surface.
The industrial exploitation of the twilight zone reveals a dangerous pattern in how humans interact with the ocean. We treat deep water as an infinite resource pool before we even map its basic ecological functions. Descending past the mesopelagic, we hit the bathopelagic zone, or the midnight zone, which stretches from 1,000 to 4,000 meters. The math on the pressure here is daunting. At 4,000 meters, hydrostatic pressure reaches 400 atmospheres, which is nearly 6,000 pounds per square inch. Sunlight is gone. The only illumination comes from bioluminescence, produced by the animals themselves. The temperature stabilizes around 4 degrees Celsius. How does an ecosystem sustain itself when the primary energy source, the sun, is removed from the equation? Life in the bathopelagic zone operates on a strict economy of scarcity. Without photosynthesis, the food chain relies on organic detritus falling from the upper layers. Scientists refer to this as marine snow. It consists of dead phytoplankton, fecal matter, and decaying animal tissue drifting down through the water column. Organisms in the midnight zone, like the gulper eel or the deep-sea anglerfish, have evolved physical traits to survive on sporadic meals. They possess weak muscles, soft skin, and expandable stomachs. Building dense bone or strong muscle requires calories that simply do not exist at 3,000 meters down. Animals here also use bioluminescence, not just for sight, but to lure in prey or find mates in the pitch black. The evolutionary pressure to conserve energy must be immense. Bioluminescence acts as a biological flashlight, but turning it on makes an animal a beacon for both mates and predators. It is a calculated risk. This brings us to a transition that feels less about a change in the water itself and more about the sheer scale of the ocean floor. At 4,000 meters, we enter the abyssopelagic zone, extending down to 6,000 meters. The name comes from a Greek root meaning bottomless. This zone covers over 80% of the ocean's total area. It is the largest living environment on the planet, yet it is often described as a biological desert. Why does life become so sparse here compared to the bathypelagic? The abyssopelagic zone is vast, flat, and brutal. Pressure ranges between 400 and 600 atmospheres. The temperature hovers just above freezing, around 1 to 2 degrees Celsius. The main reason it resembles a desert is the degradation of the food supply. By the time marine snow sinks past 4,000 meters, the nutritional value has been stripped away by microbes and scavengers higher up in the water column. The creatures that scrape out a living on the abyssal plains include sea cucumbers, brittle stars, and specialized deep-sea fish. They sift through the fine sediment for any remaining traces of carbon. It is a slow, cold existence. The sheer size of this zone makes it a massive carbon sink, trapping biological material that regulates the global climate.
Treating the abyss as just a flat expanse ignores the geological violence that creates the final layer of the ocean. The ocean floor does not end at 6,000 meters. Tectonic plates collide and subduct, tearing deep, V-shaped canyons into the Earth's crust. These trenches form the hadopelagic zone, named after Hades, the Greek god of the underworld. This zone spans from 6,000 meters down to almost 11,000 meters at the Challenger Deep in the Mariana Trench. The Hadal Zone accounts for nearly 45% of the ocean's total depth range, yet it represents less than 0.25% of the global seafloor area. The conditions here challenge the basic biological limits of carbon-based life. The Hadal Zone represents the absolute extreme of the marine environment. Water pressure in the deepest trenches exceeds 1,100 standard atmospheres. At 16,000 pounds per square inch, pressure forces water molecules into the biological structures of cells, disrupting proteins and threatening to collapse cell membranes. Vertebrate fish face a hard depth limit. Biologists estimate that beyond 8,500 meters, the pressure would alter the chemistry of fish cells so severely that they could no longer function. Snailfish found in these trenches survive by saturating their tissues with a chemical called trimethylamine N oxide, or TMAO. This molecule stabilizes proteins against the crushing weight of the water. That chemical adaptation is a brilliant biological workaround to a physics problem. It also explains why we do not see sharks or large bony fish at the bottom of the Mariana Trench. The deep ocean requires systemic chemical redesigns, not just thicker skin. Exploring these trenches requires engineering that mimics those adaptations. Humans cannot endure this space easily. The Woods Hole Oceanographic Institution partnered with NASA to develop Orpheus autonomous underwater vehicles to map the Hadal Zone. These AUVs have to navigate steep, rocky walls in total darkness while enduring pressure that would instantly crumple standard titanium submersibles. The collaboration with NASA makes sense because exploring the Hadal Zone requires the same isolation and pressure-resistant engineering as exploring a subsurface ocean on one of Jupiter's moons. The parallel to space exploration is accurate. Subduction zones in the Hadal regions are also sites of unique geological activity. While much of the Hadal food web relies on the last remnants of marine snow reaching the bottom, specific trench habitats feature hydrothermal seeps. Here, chemical energy bubbling up from the Earth's crust supports chemosynthetic bacteria. These microbes convert minerals into organic matter, forming the base of an isolated food chain, entirely divorced from the sun. In the deepest places on the planet, life finds a way to construct complex ecosystems, utilizing tectonic energy rather than solar radiation. Studying these organisms informs our understanding of how life might exist on extraterrestrial bodies. The structure of the ocean from the epipelagic down to the Hadal Zone proves that the water column is an intricate stack of distinct biomes. We move from a sun-drenched, chaotic surface driven by weather and heat down through the twilight and midnight zones, where pressure acts as an evolutionary filter. We eventually arrive at the abyssal plains and the tectonic trenches, where life relies on chemical stabilizers and geothermal energy just to keep cells intact. The physical variables of light, temperature, and pressure dictate the shape and survival of every organism in the sea. If you found this breakdown of the ocean's vertical architecture valuable, send this episode to a friend who appreciates the science of extreme environments. The Mariana Trench plunges nearly 11 kilometers into the Pacific Ocean, where the water pressure reaches 8 tons per square inch. Yet this pitch-black abyss is teeming with life. It defies basic logic. We are talking about a place deeper than Mount Everest is tall, representing the absolute extreme of our planet's geology.
The numbers are staggering when you look at the Challenger Deep, the lowest known point of the trench. The pressure down there is over 1,000 times the atmospheric pressure we experience at sea level. To put that into perspective, according to the BBC's coverage of deep-sea expeditions, it is the equivalent of 50 jumbo jets stacked on top of a single person. The temperature hovers just above freezing, typically between 1 and 4 degrees Celsius. It is an environment that, for centuries, scientists assumed was a barren wasteland, incapable of supporting any biological complexity.
Why did the scientific consensus hold that assumption for so long? It seems counterintuitive now, given what we know about extremophiles, but the barrier seemed absolute at the time.
It was a simple matter of physics and biology. Without sunlight, there is no photosynthesis, which is the foundational energy source for almost all known food webs on the surface. Combine the absolute darkness with that crushing pressure, and biologists in the late 19th and early 20th centuries reasoned that complex life was impossible. The pressure alone was thought to be a hard barrier. Proteins fold and function in very specific ways, and under extreme pressure, the molecular structures of proteins in normal animals literally collapse. They cannot maintain their shape, meaning metabolic functions cease entirely.
So the environment was assumed to be not just hostile, but sterilizing. Yet the discovery of the trench itself dates back to the 1870s, long before anyone could actually go down there to check.
The British Royal Navy ship HMS Challenger first sounded the trench during its global oceanographic expedition between 1872 and 1876. They used weeded ropes, literally dropping miles of hemp rope off the side of a wooden ship to measure the depth of the sea floor. They realized they had found something anomalously deep in the Western Pacific. But it was not until 1960 that humans actually reached the bottom to see what was truly down there.
That was the famous Trieste mission. The engineering required to survive that descent is fascinating, especially considering the technology available in the mid-20th century.
Yes, oceanographers Don Walsh and Jacques Piccard descended in the bathyscaphe Trieste. The Trieste was essentially a giant gasoline-filled float with a heavy steel sphere suspended underneath for the two-man crew. Gasoline is naturally buoyant in water, and crucially, it is an incompressible liquid, so the main float would not be crushed by the immense pressure. They spent about 5 hours slowly descending through the water column. When they finally hit the bottom, they stirred up so much fine sediment that their visibility was almost zero. But they reported seeing a flatfish resting on the seafloor.
A flatfish at 11 kilometers down? That completely contradicts the protein collapse theory you mentioned earlier.
It does, and later marine biologists heavily disputed that claim. Modern scientists believe Piccard and Walsh likely saw a sea cucumber or another type of invertebrate, because subsequent research indicates that fish cannot survive past about 8,200 meters due to that precise cellular limitation. But the sheer fact that Walsh and Piccard proved humans could reach the absolute bottom of the ocean and return alive was a monumental achievement in human exploration. They demonstrated that the pressure could be beaten with the right geometry and materials.
The gap between 1960 and the next human descent is fascinating. It took 52 years for another person to go down there, which speaks to how inherently dangerous the environment is.
James Cameron made the next crewed dive in 2012 in the Deep-Sea Challenger. It highlights how technically difficult and financially prohibitive it is to build a vehicle capable of withstanding nearly 16,000 pounds of pressure per square inch. The engineering tolerances have to be flawless. A microfracture in the hull at that depth means instant implosion. Cameron's submersible was vertically oriented, designed to drop through the water column rapidly, and it was packed with high-definition cameras to document the biology that the Trieste could not clearly see.
Let us shift to that biology, because that is where the assumptions about the trench are completely upended. If fish cannot survive at the very bottom, what exactly is thriving in the Challenger Deep?
You find organisms that look like they belong on another planet. One of the most common groups of organisms down there are xenophyophores. These are organisms adapted specifically to the abyssal and hadal zones of the ocean.
Break that down for the listener. What is a xenophyophore, and how does it function in absolute darkness?
They are single-celled organisms, similar to giant amoeba. But when I say giant, I mean they can grow up to 10 or 20 centimeters in diameter. A single cell, the size of a dinner plate. They act like vacuum cleaners on the seafloor, sifting through the sediment for organic particles that drift down from the surface, a phenomenon marine biologists call marine snow. Xenophyophores are highly adapted. They actually extract minerals and sediments from their surroundings to build fragile, intricate external skeletons called tests.
How do they survive the pressure? You mentioned 50 jumbo jets of force. A fragile skeleton built by a single cell sounds completely contradictory to that environment.
The secret is that the pressure inside their cell is exactly the same as the pressure outside. Water is largely incompressible. Because these organisms are filled with fluid that matches the density of the surrounding seawater, there is no pressure differential to crush them. If you brought them to the surface, the sudden decompression would destroy them. But down there, they are in perfect equilibrium. The skeleton does not hold back the ocean. It just provides a structural framework for the cell.
That explains the invertebrates at the very bottom. But earlier you mentioned a depth limit for fish. We do find complex vertebrate life in the upper regions of the trench, do we not?
We do, and they are remarkable. The Mariana snailfish, known scientifically as Pseudoliparus swire, holds the record for the deepest fish ever observed. They have been found at depths just past 8,100 meters. When researchers from the University of Washington first captured specimens using baited traps in 2014, they found a creature that looks nothing like the armored, terrifying monsters people associate with the deep sea. The Mariana snailfish is small, soft, and completely translucent. You can see its pinkish internal organs right through its scaleless skin.
It lacks scales entirely. It seems evolution took the opposite route of what one might expect for a high-pressure environment.
No scales and very little bone structure. Building calcium carbonate shells or dense bones is chemically incredibly difficult at extreme pressure because the compounds dissolve easily. So the snailfish adapted by becoming a gelatinous mass. It also produces specialized chemicals in its body, particularly a compound called trimethylamine N-oxide, or TMAO. These chemicals stabilizes its proteins and prevents water pressure from distorting the cellular machinery. But there is a chemical limit to how much TMAO a fish can hold in its cells without the fluid becoming toxic, and that limit is reached at about 8,200 meters. Beyond that depth, fish simply cannot exist.
The snailfish is the apex predator of its specific hadal zone, then?
It is. It feeds heavily on small crustaceans called amphipods. And because there are no larger predators that deep, the snailfish actually thrives. The Mariana Trench funnels organic matter down its steep, V-shaped slopes, so there is a heavy accumulation of food in the central trench axis. It is actually a very successful, abundant species in its habitat.
This brings us to a much darker reality about the trench. We think of it as the most remote, pristine wilderness on the planet. But recent expeditions have completely shattered that illusion.
They have. In 2019, an American explorer named Victor Vescovo broke the record for the deepest solo dive in his custom submersible, the Limiting Factor. He spent 4 hours mapping the bottom of the Challenger Deep. He discovered new species of amphipods and documented colored rocky outcrops. But the expedition made global headlines for a completely different and depressing reason.
He found garbage sitting on the seafloor?
Sitting at the absolute bottom of the ocean, nearly 11 kilometers down, Vescovo documented a plastic bag and sweet wrappers. The scientific follow-up to this discovery is even more alarming. Researchers collected amphipods from the trench during these recent dives. When they examined the digestive tracts of these deep-sea crustaceans in the laboratory, they found microplastics in a vast majority of the specimens.
So the pollution is not just sitting passively on the seafloor. It is actively being metabolized into the hadal food web.
The Hadal Zone encompasses the deepest trenches on Earth, and human waste has thoroughly integrated into it. The plastic we discard floats in the upper ocean, slowly degrades into microplastics from ultraviolet exposure and wave action, and eventually sinks. Because the Mariana Trench acts as a massive geological funnel, it collects this sinking debris. The marine snow that feeds the xenophyophores and the amphipods is now perpetually laced with synthetic polymers.
The legacy of human industrialization reached the bottom of the ocean before our cameras did. It forces a massive shift in how we view the oceans. For generations, the ocean was treated as an infinite sink. The solution to pollution is dilution. But finding a plastic grocery bag in the Challenger Deep proves that the ocean is a closed circulatory system.
Our actions on land are inextricably linked to the most isolated ecosystems on the planet. The presence of microplastics in these organisms must also impact their survival. We are talking about species that have spent millions of years evolving highly specialized adaptations to survive extreme pressure and cold. Preliminary studies suggest that these microplastics can block digestive tracts or leach toxic chemicals into the tissue of the amphipods. Because the ecosystem operates on such a slow metabolism, the cold temperatures mean biological processes move at a fraction of the speed they do on the surface. Recovery from environmental damage is equally slow. A disruption in the food chain there could take centuries to correct.
Let us talk about the geology for a moment, because the trench is not just a passive basin collecting trash and marine snow. It is a highly active tectonic zone that shapes the entire Pacific Rim.
The Mariana Trench is formed by a subduction zone. The massive, dense Pacific tectonic plate is colliding with the smaller Philippine Sea Plate, and the heavier Pacific Plate is being forced down into the Earth's mantle. That grinding, relentless descent is what pulls the seafloor down to such extreme depths. It generates earthquakes and volcanic activity along the island arcs.
And that geological activity also provides another energy source for life, entirely independent of the sun.
We see this through hydrothermal vents and cold seeps. In 2025, scientists analyzing samples from underwater mud volcanoes in the region found striking evidence of biological activity. These mud volcanoes do not spew hot lava. They ooze cold mud and fluids driven upward by the extreme tectonic pressure from the subducting plate.
What kind of life is sustained by cold, pressurized mud?
The researchers discovered fats derived from bacterial and archaeal cell membranes in a highly alkaline, toxic blue mud with a pH of 12. These microbes survive through chemosynthesis. Instead of using sunlight for energy, they produce energy by consuming sulfate and converting methane into hydrogen sulfide. They are metabolizing the chemical byproducts of the Earth's tectonic engine. It is a secondary biosphere functioning entirely independent of the surface world, hiding in the mud of the trench.
This duality of the Mariana Trench is striking. On one hand, it represents the ultimate frontier of biology and geology. It holds ancient, alien-like life forms that expand our definition of what is biologically possible. On the other hand, it serves as a grim mirror of modern human consumption.
The trench acts as a planetary archive. It archives the slow geological movement of the tectonic plates. It archives the evolutionary marvels of the snailfish and the xenophyophores. And now it is archiving our plastic waste. When future generations look at the geological strata being formed at the bottom of the Mariana Trench right now, they will find a distinct, permanent layer of synthetic polymers embedded in the sediment.
The implications for marine policy are massive. When Victor Vescovo brought back images of that plastic bag, it was meant to catalyze action. Has there been any tangible shift in how international bodies approach deep-sea conservation since that footage aired?
It has certainly amplified the discourse. The United Nations and various international marine organizations use these findings to push for stricter regulations on plastic production and waste management. In 2009, the United States established the Mariana Trench Marine National Monument, which protects the sections of the trench within its exclusive economic zone from commercial fishing and mining. But you cannot put a fence around a trench to stop sinking microplastics from global currents.
The water column is completely fluid and connected. Conservation in the deep sea requires action on land. You cannot protect the Challenger Deep without changing consumer habits in coastal and inland cities worldwide. Furthermore, there is the looming threat of deep-sea mining. Companies are looking at the abyssal plains and trenches as untapped sources for rare earth metals.
The deep ocean is rich in manganese nodules and other chemical deposits critical for modern electronics and green energy batteries. The debate right now is whether we can mine these areas without destroying ecosystems we barely understand. The baseline data we have is incredibly sparse. Every time a submersible goes down to the Mariana Trench, researchers find new species of microbes and crustaceans. If industrial mining operations commence, we risk driving organisms to extinction before they are even classified by science.
It represents a fundamental tension between exploration and exploitation. The technological advancements that allow us to finally reach the Challenger Deep and document its wonders are the exact same advancements that make it vulnerable to commercial extraction.
The limiting factor submersible proved that the deepest point on Earth is now routinely accessible. Vescovo dove down there multiple times in a matter of weeks. The door is officially open. The question moving forward is whether humanity walks through that door as careful observers and scientists, or as industrialists looking to harvest the deep.
Our relationship with the Mariana Trench has evolved from viewing it as an unfathomable void to recognizing it as a delicate, interconnected ecosystem. The fact that the Mariana snailfish thrives under the weight of 50 jumbo jets is a testament to the resilience of life. Yet that same life is entirely defenseless against a discarded candy wrapper descending from the surface. The extremes of the trench force us to confront the true reach of our environmental footprint. If you found this dive into the deepest part of our planet compelling, please share this episode with a friend.
The most abundant vertebrate on planet Earth is not the human, the chicken, or the cow, but a tiny, bizarre creature called the bristle-mouth fish that lives in the ocean's twilight zone, numbering in the quadrillions. This mesopelagic zone, a layer of water stretching across the globe between 200 and 1,000 meters deep, operates almost entirely without sunlight. Yet it holds up to 95% of the fish biomass in the ocean. We are discussing a realm that is quite literally alien to our terrestrial understanding, a place where light vanishes, but biological activity explodes.
The contrast between the sheer lack of light and the abundance of life is what makes the Twilight Zone so difficult for people to conceptualize. When we talk about an environment sitting between 200 and 1,000 meters below the surface, we are looking at water pressure that can reach up to 1,500 pounds per square inch, alongside temperatures that hover near freezing. Photosynthesis is physically impossible here. Yet, as you mentioned with the bristlemouth, this is an ecosystem bursting with life. Woods Hole Oceanographic Institution data suggests the biomass here might be 10 times higher than marine biologists previously estimated.
That discrepancy in our estimates fascinates me. How did we miss the biomass of the ocean by a factor of 10? It seems almost negligent that an entire global layer of ocean, packed with quadrillions of fish, was essentially flying under the scientific radar until recently. Is it just the depth, or is there something about the zone itself that defies traditional measurement?
It is a combination of depth, avoidance behaviors, and our reliance on specific acoustic technologies. During World War II, naval sonar operators kept picking up what they thought was the seafloor. But this seafloor would mysteriously rise toward the surface at night and sink during the day. They called it the deep scattering layer. Decades later, remotely operated vehicles revealed that this acoustic bounce was not the ocean bottom at all, but the swim bladders of trillions of mesopelagic animals. Our nets were inefficient because these creatures are highly attuned to pressure changes and light, allowing them to dodge standard sampling equipment. They literally evaded our attempts to count them.
So we were literally pinging sonar off a wall of living flesh. And that brings up the phenomenon of the migration itself. If there is no sunlight, and therefore no plant life to serve as the base of the food web, what is driving this massive vertical movement every single night?
Hunger and survival. Because there is no photosynthesis, the Twilight Zone's inhabitants must look upward for sustenance. Every evening as the sun sets, we witness the largest animal migration on Earth. Trillions of organisms, ranging from tiny zooplankton like copepods and krill to lanternfish and squid, ascend hundreds of meters to the euphotic, or sunlit zone. They feast on the rich plankton blooms under the cover of darkness to avoid visual predators. Then, before dawn, they plummet back down to the safety of the mesopelagic depths.
There is a massive ecological implication to that daily commute. These animals are eating near the surface, absorbing carbon embedded in that surface plankton, and then retreating to the depths. I read a recent statement from the Ocean Conservancy noting that these mesopelagic animals lock away between 2 and 6 gigatons of carbon at the bottom of the ocean every year. That is more than double the carbon emitted by all the cars on Earth annually. It sounds like the Twilight Zone is a giant biological carbon pump keeping our climate somewhat stable.
That is exactly what it is. The carbon transfer mechanism operates through their waste, and eventually their bodies when they die. They consume carbon-rich organisms at the surface and transport that carbon deep into the ocean. Without this daily vertical migration, the concentration of carbon dioxide in the atmosphere would be significantly higher, and surface temperatures would be far warmer. The climate regulation function of the Twilight Zone is currently one of the most critical areas of oceanographic study.
Let us shift to the biology within the zone itself, because this environment forces some spectacular adaptations. If sunlight fails to penetrate beyond a faint blue glow, the creatures must generate their own light. I have seen estimates stating that up to 90% of multicellular animals in the Twilight Zone possess some form of bioluminescence. How does an entire ecosystem operate on a biological light show? Bioluminescence is the primary currency of the Twilight Zone. It is a biochemical reaction, usually involving a light-emitting molecule called luciferin and an enzyme called luciferase that produces cold light. Down there, light is a tool used for 3 main purposes: hunting, hiding, and communicating. The dreamer anglerfish, for example, uses glowing bacteria at the end of a physical lure to attract prey directly into its jaws. The prey is drawn to the light in the pitch black, only to be snapped up. Using light to hunt makes intuitive sense. Using light to hide, however, feels paradoxical. If you are in the dark, turning on a flashlight seems like the easiest way to get eaten. How does emitting light function as camouflage? It is an elegant trick called counter-illumination. Remember that the Twilight Zone is not completely pitch black. There is a very faint residual blue light filtering down from the surface. Predators in the mesopelagic zone, such as the viperfish or the hatchetfish, often have upward-looking eyes, scanning the water above for the silhouettes of prey blocking out that faint surface light below them. To counter this, many prey animals have rows of light-producing organs called photophores along their bellies. They adjust the intensity and color of the light they emit to perfectly match the downwelling sunlight. To a predator looking up from below, the prey fish effectively turns invisible, blending seamlessly into the background. That level of evolutionary precision is staggering. The animal is continuously modulating its own biological lights to erase its shadow. But surely predators have evolved countermeasures. What happens when camouflage fails? When stealth fails, you see the startling responses. Take the Atolla jelly, often called the alarm jelly. If it is attacked or caught by a predator, it does not try to fight. Instead, it triggers a blinding, chaotic burst of bioluminescent flashes. The goal is to act as a literal burglar alarm, lighting up the surrounding water to attract an even larger predator. The hope is that the secondary predator will attack the first one, giving the jelly a chance to escape in the ensuing chaos. It is a game of mutually assured destruction, utilizing a biological strobe light. The forms these animals take are equally radical. When we look at images brought back from remotely operated vehicles, the creatures seem hallucinatory. The strawberry squid, for instance, has one normal eye and one giant bulging eye, and its skin is bright red. How does bright red skin serve any survival purpose in an environment defined by the absence of light?
The red pigmentation is a perfect example of how physics dictates biology in the deep ocean. Water absorbs different wavelengths of light at different rates. Red light, having the longest wavelength in the visible spectrum, is absorbed first, disappearing within the first few dozen meters of the ocean. By the time you reach the twilight zone, there is absolutely no red light left to reflect off objects. Therefore, an animal that is biologically red appears entirely black or invisible to predators in that environment. The strawberry squid's red coloration is a biological cloaking device.
And the asymmetrical eyes on the squid?
The large eye points upward to detect the shadows of prey against the faint surface light, while the smaller eye looks downward to spot the bioluminescent flashes of predators or prey in the abyss. It is an animal perfectly engineered to exploit the dual nature of the mesopelagic light regime.
This environment feels intensely disconnected from our reality, yet profoundly tethered to it. We have this massive biological engine regulating our climate and supporting the broader ocean food web, including commercial species like tuna, and yet it operates in utter darkness. It raises the question of vulnerability. Because it is largely unexplored and unowned, falling within the international high seas, what happens when industrial fishing turns its attention downward? That is the immediate crisis facing the Twilight Zone. As surface fisheries become depleted, there is growing commercial interest in harvesting the mesopelagic zone, particularly targeting those massive schools of lanternfish and bristlemouths. The intent is not usually for human consumption, but to grind them up into fish meal to feed farmed salmon, or to extract their oils for omega-3 supplements. The danger is that we might begin extracting millions of tons of biomass from an ecosystem before we fully understand its reproductive cycles or its role in carbon sequestration. If we collapse the Twilight Zone food web, we do not just lose bizarre fish, we potentially cripple the ocean's ability to buffer climate change. It sounds incredibly short-sighted. We would be strip mining the planet's climate control system to make cheap fish food. Fortunately, there is some movement on the conservation front. In late 2025, the International Union for the Conservation of Nature actually passed Motion 035, specifically calling for the protection of mesopelagic ecosystem integrity before any industrial exploration is authorized. It is a rare moment of preemptive conservation, rather than a reactive attempt to save an already destroyed habitat. The passing of Motion 35 is a critical step, but enforcement on the high seas is historically weak. The Twilight Zone does not belong to any single nation, which makes it a classic tragedy of the commons scenario. The scientific community is racing against commercial interests to map the zone, understand the vertical migration metrics, and quantify the exact volume of carbon locked away. We have a brief window to establish binding international treaties that protect this layer. It forces a complete reevaluation of what we consider empty space. We look out at the deep ocean and see a dark void, but between 200 and 1,000 meters down, there is a thriving, bioluminescent metropolis driving the biological rhythms of the planet. The fact that quadrillions of animals are migrating vertically every single night, pulling carbon from the atmosphere and lighting up the darkness with chemical fires, proves how deeply integrated our survival is with organisms we will never see. If you found this deep dive into the ocean's Twilight Zone compelling, share this episode with someone who appreciates the